Can somebody turn your microphone off? I think somebody's microphone is on. Okay, it's good. So just like the way we were looking at superdense coding, and teleportation is another important aspect. And people have recently done an experiments and demonstrated quantum teleportation. So as we see in this circuit diagram, so you have to teleport the whole task in front of you. You have a state psi with Alice, and somehow Alice has to send state psi or the information of state psi to Bob without sending a real quantum qubit from her side. Like, she should not send a quantum qubit, but Bob should still be able to reconstruct quantum qubit or the information of quantum qubit on his side. So that's the whole idea of quantum teleportation. It means that you are not really having a physical transfer of state, but the whole information of the state is sent to Bob, and Bob in his hand has what the state Alice had in the beginning. Okay, so that's the definition of teleportation. Quantum teleportation is teleportation of a quantum state. I don't think anybody has achieved the classical teleportation till date, because it's not possible in any ways to have a transport of something or the other without any medium between. Okay, so here simple stepwise, there is already state psi, control not gate, and Adamard, and I think we had test up to this control not gate. Once you apply a control not gate on an Alice side, Alice has 3 qubit with her. Alice has 2 qubit with her. Totally, the whole system is 3 qubit. So you can see this would be the state you have 0, 0, 0, 0, 1, 1, 1, 1, 0, and 1, 0, 1. Now, Alice applies Adamard gate. So that's up to this point. So that is what will be the output. This will be the output here. So since we don't know the state coefficients of state psi, you are writing them all as like alpha, beta, and it is here. So the moment you apply an Adamard on this, the first qubit will become 0 plus 1. The second qubit, nothing happens to the second and third qubit. And this state also will be 0 plus 1. This will be 0 minus 1. And this will be 0 minus 1. So totally, the summation of these 4 elements becomes a sum of 8 element terms. So which means that's what it will be here, because this will be 0 plus 1. And this will be alpha 0 plus 1 and the same term. Again, this will split up into 2. We have these 2 terms. Split up into 2. You have these 2 terms here. Again, this will split into 2. You have these 2 terms. So totally, you have 8 terms. But you can simply rewrite them as what is with Alice and what is it Bob. That's all. So you are rewriting them as a part of 2 qubit and 1 qubit, recombination of the same state here. So the terms with 0, 0 with Alice side are all combined together. So there is 0, 0 here, and then there is 0, 0 here. So these first and the last but one term are combined together, and you get the combination of 0, 0 with Alice and some superposition state with Bob. 0, 1 with Alice and some superposition with Bob. So 1, 0 with Alice. So now, why are we rewriting the state? Because Alice, as we said, the condition, Alice has to send quantum state. So she can't have any superposition state with her. She needs to make a measurement and have a classical information out of the state she prepares. So in this possible 1, 2, so now these 8 terms are now recombined to form as a 4 term with Alice side. So it will be 0, 0, 0, 1, 1, 0, and 1, 1. If Alice makes a measurement, that's what she does here on 2 qubits with her, she will collapse this whole state into one of these 4 possibilities. So the quantum information collapses, and Alice will have only one of those possible information on the whole system. So the moment she makes a measurement. So now we'll try to analyze after Alice makes a measurement on this state, what are the outputs and how do we interpret them? Okay. Case 1, Alice makes a measurement, that is this M point here. She gets a classical information. So when she makes a measurement, all that she will have with her is 0, 0 with 1/4 probability. But Bob's quantum state is not collapsed. That's what we mentioned when we took an example of 3-qubit partial measurements. So I think the reason why I introduced partial measurement was try to see how we can use them later on. In teleportation analysis itself, we need to use them. So the moment Alice makes a measurement on the 2 qubits with her, the state with Bob will be of this form with certain probability. So if you look at this point here, Alice makes a measurement with 0, 0. This will be the output on the Bob side. If Alice measurement is 0, 1, this will be the output on the Bob side. It will be same both the cases. But if Alice gets an output of 1, 0, Bob has a different state with him and not alpha 0 plus beta 1. I should also see here, it's not alpha 0 beta 1. Here it's alpha 1 beta 0. So there's a flip between these two. So in every output Alice has got, Bob has a different state associated with it. Okay. So in case 1, if Alice gets 0, 0, this will be an output state with Bob. Alice transmits classical bit 0, 0 to Bob. So she can send classical information. So there is no need. She's not sending any quantum state, but she sends a classical information to Bob, 0, 0. So what Bob does, because both bits are 0, 0, he does not perform either of the two possible operation, and so his qubit remains same. So he does not do anything, because Alice has sent 0, 0 and Bob does not have to do anything, and he gets back exactly what the state Alice has sent. But this is not all the time, right? Quantum state can collapse to any one of the 4 possible configuration with Alice. So Alice has no control on what state it collapses. So if Alice measurement gives 0, 1, she sends that information to Bob. But Bob now should reconstruct his state. Whenever he gets 0, 1, all that he has to do is a flip, right? It's just a flip of the states with him. So this should become 0 and this should become 1, right? And that is the condition which you are putting here. So Alice transmits the classical bit 0, 1 to Bob. Because the first transmitted bit is 0 and the second bit is 1, Bob performs a NOT operation on his qubit. He just does a flip of this operation. So this is what it does, the control NOT operation. And then the state becomes, again, the same as what was the initial state, psi. The output, exactly the same output, is recovered at Bob. So similarly, if Alice measures 1, 0, so she has to do Bob. She sends that information to Bob, and Bob knows that there will be some minus sign with him. All that he has to do is introduce this -1 flip, which is the control Z flip, which is control sigma Z, which we had seen before. So the moment she does the sigma X operation on the second controlled sigma X operation, is recovered the same state which Alice has sent. So if she gets 1, if Alice gets 1, 1, then she sends that information to Bob. Okay, so somebody's asking how Alice sends classical information. Classical information can be sent in various ways. She can even take up a telephone and then send an information. So that's why the word quantum teleportation is there here, right? You're only restricting not to send any quantum information, but you can send what we call is local operation and classical communication. So I've not introduced this term. LOCC is the terminology for it. You can do local operations on a quantum state on your side, but you can not send any quantum state. You can only send a classical information from Alice to Bob side, or from a sender to a receiver. So that's what is happening in this teleportation. But there are protocols, more complicated protocols there, where you don't try to avoid classical teleportation, classical information being sent, and those things we are not touching here. But then here, classical information is sent through some classical channel. Alice measures 1, 1. She sends that information to Bob, and Bob will be able to reconstruct by doing an operation, sigma Z gate operation, control sigma Z gate operation on his side, and reconstructs the state which has been sent here. Okay. So it might not look very dramatic, as because somebody might say, oh, you are sending classical information between Alice and Bob, but you're not sending any quantum state, but you're still reconstructing quantum state at the Bob's side. So, so here what you are trying to do is, if you have two channels, both classical and quantum, then you can ensure that with using both these channels, you can have an additional security to your protocols. So if one of them is hacked, you will get to know. So that's one of the ways people are trying to see exploit best of both the worlds, classical and the quantum world. So this one simple example of quantum teleportation, and we are trying to demonstrate that using an entangled state between Alice and Bob before, you can send two classical bits using just a single quantum state, that is a superdense coding, or you can send a quantum bit, right, by sending two classical information. So now, if you try to combine both the superdense coding and quantum teleportation, okay, so you just have to think, sit quiet and think, what is the task of both of them? So they have some relationship between them. You want to send two classical bit, you can do that by sending one quantum state. Now you want to send one quantum bit, you can do that by sending two classical bit to Bob. So it is the reverse of it. It's actually an inverse kind of problem here, right? Alice sends two classical bits here, Bob reconstructs quantum state. In the previous example which we took, Alice sends only a quantum bit, Bob reconstructs two classical bits. So it's the physical interpretation and what they're doing looks very different, but mathematically, if you're trying to look, it is a reverse of that problem. If that is possible, the other way should also be possible, and that's exactly what we are shown here. And both of them has been done using an shared entangled state. Here we took an example of just one form of entanglement. Now entanglement need not be extremely strong. There can be various different forms of entanglement. Okay, so there can be various different forms of entanglement, and you may not get 100% accuracy when you have a weak entanglement between them. So all those things have been studied and people try to look at this problem. Okay, so we took these two examples and we have looked, and now next is the most other important point, right? For any task to do any, I mean, what do you mean by algorithm? For us, algorithm means a set of operations which solves your problem. You might have a query, then you develop a protocol, and then you look at it. Here, I'm just giving you a simple analogy of a probabilistic algorithm versus quantum algorithm, or what we call today as a classical algorithms. And then there can be many classical algorithms which takes probabilistic route, and then there's a quantum algorithm. So that's what it's been here. Left side is we are seeing you have some particular state, and then you have multiple possible probabilities. You get more multiple outputs. From that output, you want to explore which one is your solution. And these are all like all probabilities of it. So simple example would be a classical random walk, where you toss a coin, you go to the left or right. But then if you have multiple or more than one possible solutions for it, then you try to explore all possible solutions and then see, is this the solution you want? And you look at it. Now, quantum algorithms, as yesterday we said, or even today we have been looking at amplitudes. If you are not looking at amplitudes, if you are trying to take only the measurements and then look at the outputs, this is a modulus square of the amplitudes, then they both are same. When you do quantum operation, you make a measurement, you again do a next operation, you make a measurement. So you're not going to get any quantum states in it. So you'll only get a classical equivalent of it. So if you are making measurements, no quantum advantage comes. So this is just an example of how you are trying to start looking at algorithm. But if you are dealing with only amplitudes and not with the amplitude squares and not with the probabilities, then they are not equivalent here, because even in all previous examples we looked, there were Hadamard operators. So why was it that we could get rid of some terms and then get reconstruct the state we want. Like, for example, we said alpha when a Bob gets back some state. So there are some kind of negative signs which we got are causing some destructive interference and constructive interference. So in this setup, we can devise your amplitudes. We can define your operator such that the coefficient values of amplitudes for which you don't want that to be a solution, or you're not thinking that as your solution will be negative values. You can have a destructive interference and you can minimize hitting the spots which are not your solutions, and you can amplify hitting the targets which are your solutions. So the negative signs which can come across along with your amplitudes can play a very important role in reducing the chances of going to a wrong solutions and increasing the chances of going to a correct solutions. So that's how most of the algorithms are designed. So we see quantum advantage because of those constructive and destructive interference. Okay, we'll see some of the examples with it. So there is no interference in this states in this way of approach, with probabilistic approach, but there is an interference in this amplitude approach of the quantum state. A simple example is this. We actually did this. I'm again repeating with an explicit way of looking at it. There is a quantum state 0. We do an Hadamard operation on it. You get a superposition state. But the moment you get a superposition state, you make a measurement. Then it collapses again to 0 or 1 state. Now again you apply an Hadamard operator, then you are going to get a probability. But because you have collapsed here, we don't know whether it was 0 or 1. You end up having the possibility of being in this superposition 0 plus 1 or 0 minus 1 with off probability after you apply an Hadamard. Again, the moment you make a measurement here, then you are either getting 0 or 1 with off probability. So this is a probabilistic way when you don't have any interference here. Just with a simple Hadamard, we can actually show interference here. You can see 0, you apply an Hadamard operator. So it means that I'm getting a superposition of these two states. Now that is psi1. Now you don't make measurement. Like here we have introduced measurement, but here we don't have measurement. Again, you apply Hadamard on the same state. So here you can see Hadamard on this and Hadamard on this. You're going to get 1 by root 2. Again, this will be in superposition of the terms. Again, this term will also be in superposition of these two terms. So what will happen to this? Which means you have this term and this term adding up. Then you have this term and this term cancelling with each of them. So this cancelling terms, which means that 1 by 2 of 1 and 1 by 2 of 1 cancels, and your output will be state 0. This is what we call a destructive interference. In fact, we did this before. We did this Hadamard operation. I told, Hadamard operation, and again an Hadamard operation, you're going to get back the same state, which means that it's not undergoing any change. It has actually undergone change. So some changes happened, but the destructive interference is giving you back the same state which you started, state 0. So a simple 2 times Hadamard operation shows that there is some interference in a quantum state evolution. These are things which we call as, this is destructive. So it means that what has happened is destructive interference of state 1 and a constructive interference of state 0. So this is with simple Hadamard operation. Now, if you are taking complicated set of quantum gates, and then you want to see one of the state as your solution, then you can always identify set of gate operations such that for all the states which are not your solution, you start making them have destructive interference. For the states for which you are trying to find a solution or where the solution should be, you design your set of operations so that you have a constructive interference, right? So this is just an example of how a basic element of interference coming in algorithms to help you to find the desired solution which you want. Okay. So with this, we'll try to take one simple algorithm. I think in this slide, every step is explicitly introduced so that, since the boards may not be very clear to everybody, and probably writing it also becomes cumbersome. So this is a phase kickback to a control register. So this is not a complete algorithm, but it actually is one of the simple step of trying to say an algorithm. I'm going to say what you mean by control register. So it means that you have some registrar with you, right? But there is another. So here you can see two things, 2 qubits. This is 1 qubit. There is another qubit. There are 2 qubit system. But now this is your control registrar. This is another system or another qubit for which you don't want to destroy this. I don't want to do anything to this state, but I still want to get to know what is the information or a phase of this state. Okay, we are only trying to extract partial information. The algorithms can be complicated, but in the simple algorithm, what I want to know is whether the sign between 0 and 1 is plus or minus. That is the task of this. Phase is going to be kicked back to the control register. So simply, without even destroying the state, I want to keep. So now here is a simple example. I have this state and I apply a control NOT gate on this. Nothing is going to happen because my control register is state 0. The state remains simply the same. But now here is another modified example. If my control register is 1, then there is a state, another one, from which you want to extract information. If I apply a control NOT gate on the system, then 1 0 becomes 1 1, 1 1 becomes 1 0, right? So it means that I'm just rewriting that as an output here. You take a -1 sign, then you are again reconstruct, you got back the same thing. There is a -1 sign which has come out of this state, and this -1 sign is now with the control registrar. So now what has this control NOT gate done? Control NOT gate on a 2 qubit system has extracted the information of the sign in this state without destroying this. Because if the moment you make a measurement, you are losing the state, but you don't want to destroy this quantum state. You still want to keep the way it is, and extract an information of this one. This is actually a small, simple step of phase estimation algorithm, what we call. And I will again say about phase estimation algorithm later on. But now this is only saying that if my control register is in state 0, this is what I'm going to get as an output. But if my control register is in state 1, this is what I'm going to get as an output. But I can have my control register in superposition also. This is something which I have with me. This is not what I have control, but this is what I have with me as a control one. Now, if I do a control NOT gate operation on this, which means that this 2 and 2 terms is going to give me totally 4 terms. And if you do a control NOT gate, then you're going to get an output of controlled register with you in this form. So you will have a minus sign which has come back to you. So again here, without making any measurement on your register, okay. So here, I think some question is there. What is that after? Okay, so somebody asked and somebody has answered it. Sorry, I think so. Somebody has asked how you got this minus sign, but here I'm saying 1 0 becomes 1 1, and then 1 1 becomes 1 0. All that you are doing is you are pushing this to the front and taking the minus sign out. That's all. -1 sign is taken out, and suddenly the moment you take -1 common, you will end up getting the same state as what it was before for the registrar which is not under your control. So now taking this, instead of saying that explicitly my control register is 0 or 1, I can have my control register in a simple representation. It can be 0 or 1. So now it is simply of this form. If this is 0 or this is 1, I can just write it as a value of power. If -1 to the power of 0 is 0, so it means that 0 0 will be the same thing as my first output what we got. But if this is 1, Then I'm going to get minus 1 to the power of 1, which will be minus sign. I'm going to get back what is there in the second row. And you can take it in a more generic form. So the idea is very simple here. Without destroying the second qubit, you want to get an information of the phase between these two states on the first qubit. So that's all. So you have alpha 0, 0 plus alpha 1, 1. Again, you do a control NOT gate and you're going to get back. The Z operation on control qubit gets a phase kickback. It looks very simple. And what is it doing? But then, see, you are not destroying and you're getting an information of that state. That's what I meant. And it is an important thing, right? Without destroying. So now, more generalized form of the same thing, right? That's what I said. Once you want to I didn't want it to directly introduce a complicated way of writing all these operations, but this complicated formalism of writing them is nothing but the same thing what we have shown here with an explicit example. You have a registrar with you, a control registrar, and another registrar which you don't have control over it, and you're extracting information. So why are these kinds of state important? Which means you don't want to destroy quantum state, you want to get a phase information of it. After you get a phase information of it, then you can define an operation depending on that. See, in your previous examples, we took teleportation, and then where you make a measurement, you destroy quantum state, depending on the output you get, you define the next operation. But here, you don't have to destroy. You can get a phase information. Depending on the information of the phase, you can define the next operation on a series of operations you want in your algorithm. Okay, so that's one of the simple way of, or the simple applications of it. So more general 2-qubit operation can be defined as this: any arbitrary function, 0 and 1. That's what it does, right? If you have state, we are only talking about qubits. It only has 2 levels in superposition. Output will also be mapped into 0 and 1, which means that any unitary operation, in the previous example, we only took control NOT gate. It's a unitary operation, but it can be any unitary operation on a 2-qubit system, X and 1, where you have control and then you have some state which it modifies. You can always get a phase kickback on this kinds of operation. So it does this modification, but you can get back because of this X value, and then the function operations on it, you get back. What does that mean? This only says addition of 0 or 1 or 1 or 0. In fact, this happened, the same thing happened in the last example we took here. Somebody asked, how did you get this minus 1 sign? Because 0 became 1 and 1 became 0. But because you took the minus sign out, you ended up recovering the same state as it was with the state here. Here, minus 1, you took it out and you end up having the same state here. The same thing which is written here in a more generic form. Your f of x can be 0 or 1 depending on the value here. You will end up having the things coming out here. So you are in a unitary operation on this state. Instead of having control NOT here, we are having a common general unitary operation here. It does this form. I mean, you are rewriting them as an operator on the combined system. So it can be 0 plus f of x, if f of x can be a flip or a control NOT or whatever operations you define, and then again general form here. Depending on the two cases, f of x can be 0 or f of x can be 1. So it's an operation, but still the impact of the effective output of that operation is it becomes 0 or 1. So it means that it will be 0 addition modulo 0 or 0 addition modulo 1, right? So now the same thing which is now rewritten, or the same thing is written here, and then we are trying to take those things as a common factor out, because that's what we said, f of x is good 0 or 1, and if you write them as minus 1 to the power of f of x, it's just a rewriting of the same state in a more generic form here. And you have a function here, instead of c0, we said you are having a general function f of x. So it's minus 1 to the power of f of x, and then you have recovered back what it was there. The phase has come back in the form in the system. So when control qubit is in superposition, again, the same thing can be rewritten where you are writing it as f of 0 or f of 1 explicitly. You can notice that the state of a secondary star is an eigenvector of u of x, and an eigenvalue is kicked back. The eigenvalue is, it means that the coefficient values which you have is kicked back to your control register. This technique of inputting an eigenstate to a target qubit of an operator and associating with eigenvalue on the state of the control register will be very useful in eigenvalue estimations. Or it means that you want to have an estimation of the eigenvalues of the state. Eigenvalues and eigenvectors, I didn't introduce them, but these are the basic way of defining the coefficients of the quantum states and the quantum states. So quantum states are, these are like, I can call this as one eigenvectors, and the coefficients of them will be the eigenvalues, right, of any quantum state sum. Alpha, beta, here also alpha 1 and alpha 2 are the eigenvalues, and these are 0 and 1 are the eigenvectors. So you are trying to estimate the eigenvalues of the quantum state without making a measurement of them. So this has implications in some algorithms coming in which we discuss later on. So I looked at, we are taking an example here, a simple example of estimating whether you have a -1 or a +1 in between 0 and 1. That's what we looked at here. In between 0 and 1, you want to estimate whether this is minus or plus sign, nothing more than that. But in general, you can actually estimate any values. So a simple here, a quantum phase estimation, it means that Hadamard operation is a self-inverse that we actually looked at it, right? In fact, in one of the examples we took, we said Hadamard operator, and again an Hadamard operator will give back the same initial state which you had in the beginning, h on x, and again h on that output, we are going to give back x. But here we are trying to write them in a more general form, because once you start writing algorithms, we can't write them all in a long extended form. So you want to try to write them in a compact form, in a large number of qubits. So I want to define an action of Hadamard operator on a general state. I don't know whether it's x, 0, or it can be any superposition. So on any general state x, an Hadamard operator can simply be written as 1 by root 2 0 and minus 1 to the power of x and 1. Now we can plug in here, right? If x is 0, then this is 0, then it is 0 plus 1. If x is 1, then this will be 0 minus 1, because minus 1 to the power of 1 is minus 1. So this will become 0 minus 1. So irrespective of explicit value of x, this output represents a general effect of Hadamard operation on any quantum state x. But this can still be simplified, right? We are writing this as a summation term. Minus 1 by root 2 is common. We have kept it here. But now we are writing it as a summation of minus 1 to the power of x comma y, xy, sorry, and the state y. Now, my state y is can span between 0 and 1, which means I will have two terms here. It can be 0 and plus 1. But depending on the value of x and y, my coefficient value gets fixed. So which means if my input is 0 and my y is 0, then these two will become 0, 0. This will be 0, 0 and y will be 0. So it will be 0. But if my x is 1 and y is 1, and this will be 1, 1 and minus 1 term will come in. So the same state can be rewritten as a summation in a summation form with only variable values without any explicit fixed value for vector notation, right? So, and an Hadamard operator on that again gives back to the same thing. Why we are writing this is only to say that you can have a very generic term and the phase component can be extracted out, and you can always estimate those phase values without destroying the quantum state here. The value of x is encoded into a relative phase between 0 and 1. So now see here, that's what it means. The value of x is encoded in the phase term. So I have a state x I don't make measurement on it or anything, but that information is encoded in the phase term. Phase term is something which we get out of measurement, so we can always have the information of the state by getting it into a phase term. So Hadamard operation on n qubit basis is given by this form. In a general, not one qubit. I'm saying now we can take a large number of qubit system, 10 qubit, 4 qubit, or an 100 qubit quantum computers. An Hadamard operator can be defined on them like this in a more generic form where x and y's are a long series of powers. So what we wrote for simple 1 qubit here can be generalized into a large n qubit system, and the information about the value of x can be encoded in the phase of -1 to the power of x dot y. So this is a general representation of them. And here, -1 to the power of xy in this phase of specific form. A more general form of phase will be e to the power of 2 pi I omega. And those things can also be estimated using these approaches. Here we are only trying to estimate the -1 +1 sign in a more general form, but in a complicated algorithms, you can start constructing them and estimate them looking at this. So this is a simple way of looking at the phase estimation algorithm. Okay. So now we looked at super dense coding, we looked at teleportation, and we are trying to see how you get a phase kickback simply without even destroying or doing any damage to your quantum state, or what we call a target state and control state, this controlled qubit and target qubit. That's how we call. So in a phase kickback, we had these two, right? The first one, we call it as a control register, and this will be a target register. You don't want to destroy target register, but you can still get, and that also we looked into. And a more general form of that can be extended as a phase estimation algorithm. Okay, so somebody asked this question factually, where was this term? Okay. So can you speak up and say what was the... So
what does the last line mean?
Which, okay, you mean telling the n qubit Hadamard operation is not able to fully access information? Is that what you mean?
Yes.
Okay. So n qubit Hadamard operation is not able to fully access information that is encoded in a more general way. What I'm trying to say here is, we took Hadamard operator here and we are trying to get the information of phase x into the power here. All that it is trying to say is, you are going to get -1 to the power of x dot y as an information. You can't, it means that it is restricting you to say whether your omega is 0 or 1. I mean, which corresponds to specific binary value. It can't estimate any general value of omega. For that, you can't use Hadamard, you need to use some other operation. That's what it means. It only tries to say -1 or +1. All that I said before also, you can estimate, or you can have an information of whether the phase between the first or the 0 and 1 is -1 or +1, and that information you can get, but you can't get the information of a very general phase using an Hadamard operation. You can do that using a more complicated algorithm. That's what it means. Using an n qubit Hadamard operation, you can't get a more general phase estimation. You can get a phase estimation of only minus or plus sign. Okay, so there is an algorithm, quantum phase estimation algorithm, which can estimate any value of omega. But then you can't use Hadamard alone. With Hadamard you can use, but that becomes more and more complicated, and it won't be. I think doing it with the slides or doing with board in a class would be more appropriate, and that itself requires a complete 1 hour or even more to do that algorithm. But that is one of the important. I don't know whether you are all familiar with. I'm going to touch that algorithm. I define definition of that algorithm in the next slide. That is one of the important things. In fact, it's here itself. So I can say the two important algorithms which defined the root for quantum computers itself are the factoring and search algorithm. So Shor's factoring algorithm is one of the algorithms which was first proposed in 1994. It's a very complicated, but it took a long, many years for Shor to develop, and then for even people to verify and understand the real importance of it. What it says is that if you are having two prime numbers, and if you combine them, you get a number, right? So finding the prime factor of n, given n, finding p and q is the most complicated process in any classical algorithm. In fact, it is actually said for large numbers, no existing classical computing capacity today can do it in the real time of it. So that's why we call all of our security, or which we call RSA cryptography, or various of those things, or factoring itself is used as security for our informations. But what Shor said was, using quantum algorithms, quantum approach, Shor's factoring algorithm. Shor's factoring algorithm has multiple steps. Phase estimation is also one of them in it, and that's why we only defined a bounded phase estimation. But a general phase estimation is also one of the steps in Shor factoring. It says that you can easily factor any given large number if you are using quantum states in it. So a rough or naive idea of it is that if p and q are the two prime factors, if you can represent, you take a large qubit system and you represent them all in superposition of all possible values, you define some conditions such that you are having a constructive interference to the value of p or q and destructive interference on other places because of superposition and simultaneously exploring all possibilities. Shor algorithm shows that you can find the value of p or q very quickly using quantum approach. So this is a definition of it. In fact, I'm actually not discussing or explaining the whole steps of Shor's factoring algorithm. I think there are sessions probably later on to look at this cryptography and then factor, where I guess that's going to be addressed. But the whole idea of Shor's factoring algorithm is that the quantum thing does it at order of n squares times compared to the best classical known algorithm. So no classical way you can do that. And that's one of the things which triggered that quantum computers, if somebody builds a quantum computer of large number of qubits, then all security system today can be hacked, because it can do things faster and factor things and then get all our pins, which are all encoded in the forms of prime numbers, and the security system can be compromised completely. So that's one of the race. That's why people are racing towards building quantum computers. Whoever builds first will have an edge over the information existing in the world. Okay. Another important algorithm, which again laid a foundation to the field of quantum computing, is Grover's search algorithm. Okay. So it says that if you have an unsorted database, here there is an example, you want to find out, in fact, there is a whole set of information available. How quickly can you find this one particular place, right? That's exactly what it means, that if finding I such that xi is equal to 1. I want to find out a position where my state I is 1. So in normal circumstances, you have to go to each and every place, and that's how classical algorithms are designed, is that, I mean, if I'm trying to give a Google search, I'm going to search for something, or what it does is it tries to quickly try to go to every place and then try to find out where you are going to see. The best possible way is n queries required. Even the best, I could say that n by 2, because if you do half of them, you will get to know, you have a very high chance of finding that, this is the place where on an average that you have the information which you want. But what Grover search algorithm said is, all that you need to do is you need to just have root n queries needed to search for this information, which is quadratically faster than any classical known algorithm existing today. So that's what then we said, Grover search algorithm can search things faster than any classical algorithm which exists. So the steps of Grover search algorithm are in this next slide. Okay, one of the simple example which we look at unsorted database or a sorted database. So there are two ways of looking at it, right? most of you might be familiar with the telephone directories. So you will have phone number names associated with the telephone numbers. So if I'm talking about names which has been altered, they're all sorted. So all the information in telephone directories are sorted in an alphabetical order. So now if I say, please a telephone number of so and so name, it's very easy for us because we know it's in alphabetical order. We'll very quickly zero down into pages where that particular all names starting with that particular letters are there, and we very quickly find out, and this is the phone number of that particular. Now, if I give a phone number of somebody and then ask you to find out what is the name of this person who owns this phone, then it is very, very difficult because that is an unsorted database because your phone numbers are not sorted in any order. Only names are sorted in an order. So that's where we are talking about where Grover's algorithms can help faster than the classical algorithm. So now, how do we look at it? It means that every telephone number can be one of your quantum state. And psi omega is what I've just marked one particular state. And that is the phone number we need to identify where that phone numbers exist in the telephone directory. And corresponding name is what we want to get. Once we get the phone number where it exists, then you can always find out. Classically, order of n queries are required. Grover said you can do that very quickly. So now what are the steps to that? So now what we are doing is all the information in a telephone directory is now converted or restructured as a quantum state. So that's all. Right? That's exactly what is happening even in all our searches and all our computers. We have the information there and we are storing them all in terms of classical bits. And then we are trying to search for a pattern in the classical bits. And then that's how we are getting all our output from our search. So what are the steps to look at it? These are the steps for Grover search algorithm, which means that given n number of data, large data, you can rewrite them as a quantum states in superposition, equal superposition of all possibilities. So, or you can even create, that's what when we said Hadamard operator on an n-qubit system, you can create a state of this particular form, S where 1 by root n summation of 0 to n and n x. So, once you prepare an equal superposition state of all possibilities, then you repeat I think you might all have been familiar with the word oracle, which means a set of operation, a subset of operation here. You do these two sets of operations. You apply an operator UW and another operator US, and then make a measurement. That's all. Okay. Now this looks at what are these operations, what is it doing physically to the state. Things might look complicated. We will dissect each step in the next slide. But all that it tries to say is, given all the information, like if I would, for example, to simply say I have only 4 numbers or 4 telephone numbers. I want to find out which telephone number associates is corresponding to some name. So now I can use 2 qubits, write them as a superposition. Any 2 qubit can be written as a superposition of 4 possible configurations, right? So now those 4 telephone numbers, I label them in correspondence to 4 possible quantum states which exist. So that's what we are writing here, superposition of those 4 possible states. In that, omega is my mark state. S is all possible state. That's exactly what we write on. S is superposition of all possible state. In that, there is one state which is omega. For that, you are doing these operations. I'm going in the next slide. We have an explicit expression of this operation and what it does to that. Right? We can come back to this slide again once you look at this picture. So this R is this operator, omega W, the reflection. So you see this. I know I said, for example, we simply take some 7, 0, 1, 2, 3, 4, 5, 6, 7 are the number of database exists. Equal superposition of all of them. And then you apply US, which is a rotation operator, which means only for a mark state, It means that somewhere its size, you have all the superposition state. For that marked state, I want to introduce some -1 phase. For the rest, everything is fine. That's what we are doing here. This operator, this is for corresponding to position 0, and this is corresponding to position 1. This is corresponding to position 2. So for all the states, I'm not worried. My interest is to only identify the phone number, the position where there is this phone number, right? So all that I'm going to do is this -1 phase, which flips the state into this. And then the next step is this diffusion operator. That's what we call. So now we see this D and R. You see, I mean, you don't have to worry the detail in this operator. You can even look at the picture, which I'm showing as an output of that operations on the state. So we'll go back to this here. Here I have this one operator which only introduces minus sign to the marked position. That's all. It might look complicated. Identity -2 omega, but it introduces -1 sign to the place where you want to find an object, right? And this is what we call a diffusion operator, rearranges the state. These are the two operations which comes in here. This introduces minus sign, and this introduces diffusion, which means it flips and takes away, means introduces destructive interference at all this position and constructive interference at this one explicit mark position. Here you can see it's the same. No, it's not doing anything uniquely here. It's the same operation at all the position, but just because there was negative sign which was introduced to this R by this R on this particular state, that negative sign here, it's going to affect everything. Everywhere it reduces the amplitude at all these positions, but here it increases the amplitude at this position. So you have to iterate this few times, square root of n times. It rotates the phase. It means that it flips and then amplifies the phase here. And an average amplitude at each time step increases by 1/√n times at that particular mark position. And then you implement, it means that if you are applying √n times those two operations in combination, you will end up having almost 1 amplitude at the position where your marked data exist, and at all other positions, it's almost will become equivalent to 0. We have only taken one rotation here and we have shown the amplitude, increase in amplitude. So we are kind of getting a constructive interference here, and that -1 phase is decreasing the states which are getting here. Okay, so I think I would take some questions here before we go to the next stage. If there is any question, please.
Sir, if any participants have doubts, you can ask.
Sir, how is the negative sign decided in rotation phase?
Okay, so here, let's say in this operator here, right? So what we are trying to say, okay, I mean, to make things simplified, I'm trying to fix a position here. But each position only means a quantum state, what I am going to find as a marked one. So here I have a superposition of all possibilities, but I know what data I want to find. That alone is in this form omega. Only for that omega you are going to get a minus sign here. So if I rewrite this, if you see here, 1 1 1 1 identity, right? So this is an identity operator, the matrix, and this will be -2 omega and omega. So which means that only for one particular mark state you are going to have a -1 sign. So identity and -2, which means that can you imagine that this is all first element is an identity at all the position, and this is 0 at all diagonal element and -2 only at this particular mark state. So both of them are diagonal matrix
Yes, sir.
here, right? A diagonal matrix, first one is -1 at all positions. The second matrix is 0, 0 at all position. Only at the mark position you have -2. So 1 minus 2 is -1. That's how you end up getting. So this is not a position, physical position explicitly. Each element in the diagonal term represents a quantum state. So we are only trying to find a quantum state and then amplify an amplitude further. The moment you make a measurement, you have to get it. So just to make things, how the amplification and rotation coming, we are labeling them physically here. Okay. Okay. So yeah. So next, is there any other?
Any other participants, sir?
Right? Hello. Yes. Okay. So if there's no other question, we'll proceed to the next. So this is something which, in fact, one of the Grover's search algorithm, the title for it was very interesting. I think the paper which Professor Grover wrote said, "Searching for a needle in a haystack." In fact, how you have an haystack somewhere and then there is some needle there, and how quickly you can search. And that's how we titled. And it's very neat algorithm to show how you can have a construct. So it looks like a simple algorithm, but then you can apply it to various physical problems, right? So it's like amplifying the solutions you want and have a destructive interference everywhere. Phase kickback PPT. So somebody wants to look at the phase kickback. Okay. So is this what you're trying to look? Simply a phase kickback. Is this the slide you wanted to see? Oh, okay, the next one. This one, is it? So I think after my lectures, I'm going to put all my yesterday's and today's slides together as a single PDF file or as a 2 PDF file and then send it across to Mahalakshmi Madam, and you can take it from her. Okay, so, and if there is some queries, you can always write an email to me and I can see if I can be of some help. But the books will have, the 2 books which I referred to also will have all these details. Okay. So it's good. It will be good for you to work out few steps in between to get to start appreciating them more and to look at it. Okay. So there are different ways of defining, making things simpler. I'm not looking at the geometric ways of looking at this. But now I will try to get to somebody was asking in the morning, and then now, which is important to say, what is the physical status? Are we just doing mathematics of it? Or what are the progress which has happened? This is a result from a quantum computers, right? On a 53 qubit quantum computers in University of Maryland. Each row defines some set of operations, and this is an output. Sorry, I think it's you can say first line represents first set of operations, and that's a result of a measurement. The second set, from measurements, you kind of try to make an imputation of it. Sorry, okay, there was some slide which was come in between. So there are different physical systems for which one can think of encoding quantum states. So you can have a physical system here, A and B, no photon, and having a photon itself can be your quantum state, 0 and 1, right? You are sending a photon, there will be 2 paths to send a photon, and we call it as a dual rate encoding. That itself can be your qubit. Or it can be a polarization. If I'm taking photon as your qubit, it can be an horizontal and vertical polarization. See, this is what V and H. This can be my 0, and this can be 1, or another way. If you're taking photons, that's how you represent your horizontal vertical polarization on a Bloch sphere. And this is 0, this is 1, this is superposition states, any superposition state. You can take beam splitter. I think yesterday's first talk you might have got an idea of photon going through a beam splitter, and there will be in superposition of going in two paths. Which path encoding? Right? It can be a mode encoding, or it can be polarization encoding, or it can be a part encoding. You can use any possible ways. I know in photon itself, we are giving you three possible ways. In fact, actually A, B, free space, and then again polarization, dual rail, four possible ways of encoding as qubits. Top and bottom can be your 0 and 1. H and 1 can be 0 and 1. And look at it. So similar way, once you decide how you are doing encoding, then you start defining all these gates using optical components. Right? That's one. Now, in a current day scenario, today, nothing can be said as the most efficient quantum computers. People have over time, different quantum computers have shown different edges. Nuclear spin in NMR is one of the earliest quantum computers which was shown to do some implementation. So some algorithms were implemented on it, and it was demonstrated that quantum computers can be built. And ion trap system. So we'll discuss all this possible. I mean, how do they look physically today, and how are the people envisioning building quantum hardwares? So superconducting circuits are also used as quantum qubits, and people are doing experiments. Cold atoms, which means that atoms are trapped in a vacuum, and then you manipulate the states of atom, and then you can implement quantum gates on it and algorithms. People have demonstrated small scales of it. There are also silicon-based quantum computers which people are thinking of, where you're using spins of semiconductors and then trying to do operations. Okay, so photon-based systems, which I said, dual rail, polarization, and those things people are trying to explore and build. So there's one simple example here. When we said nuclear magnetic resonance system, this is nothing but your MRI machines, right? So MRI machines are not okay. So NMR, nuclear magnetic resonance in a sophisticated form, is the medical imaging MRI machines. If you use the word nuclear in that machine, people would get panicking. So that's why they don't use the word nuclear there. And all that it says is, you can take any chemical complexes. This one example of a chemical complex, which is perfluorobutadiene iron complex. You don't have to worry about any chemical name here, but this is also called as molecular complex, where you control hydrogen atoms, or you can control electrons or the nuclear spins of those molecules, and doing some manipulations on them, you can implement quantum gates. So all that you are doing is you use a magnetic fields to control the nuclear spins of them, and then do a number 5 fluorine atoms, nuclear spins, and 2 carbon atoms, right? So I've just totally 13 atoms are there. So you can implement some, it's like 5 plus 7. This totally 7 qubit system. So this represents a 7 qubit system. So you can take a 7 qubit system, control the nuclear spins on them using radio pulses. You can make them interact and then do some action. So source factoring, it's a simple one. I said you can always say that factoring 15 is not a very difficult problem. It's 3 into 5. We all know this answers. But what was done, it was done quite some years back. What was done was, you are defining quantum operations and logic gates on them, and then you used quantum logic gates to get an output of it. It means all that it demonstrated was, if you can scale them now, you can do a larger complicated numbers. But NMR machine has a complications. It means that you can't find a really large, complicated, complex molecule for which you can design and do operations. So you need to have a very limited approach of it, what we call as a prototype approach. But it helped in implementing most of the early algorithms, and say that quantum computers can be built. So next is an ion qubit. So this is one of the most successful quantum missions today, which means that it has a good coherence time. I didn't use this word before, but what I say is that quantum states can get disturbed very quickly. But in these missions, people have already demonstrated that you can have 53 qubits and then do some set of operations. This is an example of doing some operations and the result output, a complex qubit organization. Each row has 53 trapped qubits, and 0, it means that seeing a dot there and not seeing a dot indicates state 0 and 1 upon measurements. And finally, in any mission, all that you have at the end is a measurement output, and from that you interpret your result. So this has been done, and this is another form of quantum computers which has been built today, which is all superconducting qubits, where you are having a superconducting circuits. Current flowing direction are treated as state 0 and state 1. Like you can see here, a circulating current. If the current is circulated in this axis, in one of the directions, you call it as spin down, which can be 0, and another axis which is spin up, that will be spin 1. And you can control them and all. All this is a big machine. All this, but it's a only small few qubit system. It's a cryogenic system that to be maintained at a very, very low temperature. It looks very cumbersome. It takes very difficult to build them, and people are building. All that we can do is we can imagine them like the way vacuum tube classical machines, quantum computers were there in 1950s and 60s. It did not, I think with years, quantum computers may not be as complicated as this physically. It can be more compact, and probably it can do a lot more interesting things. But these machines have been built, and some algorithms have been implemented on them to show that in principle, you can start building and scaling up the machines. So IBM quantum computers, which has given cloud access to some of the qubits, are building it on superconducting qubits. Okay, so this is the current, I think the last year's picture of IBM superconducting qubits. Here, people have add 16 qubits, 7 qubits, which have been built. These are all like wiring to control those qubits and then doing operations. You send are radio frequency pulses and then activate one qubit. It means that you activate a current flowing in one particular direction or other direction or in superposition. All those things are controlled by sending currents on them. But the chip as such is very small. It's in between. So it's only the control system which are big, really big. All this is vacuum and a control system. The chip as such, a qubit chip is as such is very small, and they are not every qubit is connected to every qubit, but some qubits are connected to one another, and people are building quantum circuits on it. So what is interesting in the current day system is that, you know, in our algorithm, when we defined teleportation or when we defined some gates, we just took a mathematical form, and then we wrote quantum gates for it. But for the current days quantum computers, few qubit quantum computers which exist, you simply can't implement those gates which we have done as an exercises. You have another restriction to that, connectivity restrictions. In these architectures, not all qubits are connected to one another. You might have to redesign gates specifically suitable, gate operations specifically suitable for these quantum computers. That's what people are doing. In fact, we are working on project with University of Maryland, where we try to work on building specific quantum gates combinations to be implemented on their machines, because the architecture is different. So general algorithm exists, but how do you map them into their system? So for IBM mission, connectivities are different. People have to really redesign gates for them and to look at it. So there are lots of open problems to look at and challenges to be handled the current way, until we have a more generic universal quantum computers available, which may take many years from now. Okay, so this is another structure of how people are trying to build quantum qubits, which are cold atoms. So you take some of these ultra cold atoms, which are alkali atoms. You can use laser techniques to cool them in a vacuum and then trap them at some point, and then you try to control their internal energy levels. So you can have, that's what you can, array of qubits. You can have a cold atom reservoir in a vacuum chamber, and then you can use some laser pulses to control each atom independently, change the states of them. Okay, so you can change the states of them and then say this is 0, this is 1, or you can make them interact. In fact, people even can take items from this point to this time, bring them closer together and take them apart and do some operations. But all these things are really physically demanding, and having atoms to be cooled at vacuum and then trapped itself take years for them to build, and small variations in temperature or some fluctuation, some physical noises can destroy those atoms. So they're very fragile and takes time to construct and build them. And they may not, once you have trapped and got atoms at some point, you can only do few set of operations, they're going to destroy. And that's the stage people are there currently. This is also another term. Why am I saying all these things? It means that there are different possible hardwares people are exploring. Nobody knows which one will be the ultimate one which can be scaled and effectively used. Everybody have their own advantages and disadvantages. As of now, ion trap qubits have better advantages than the other, more advantages than the others, but with time we don't know, something else can come up in between. This is another way of trying to look at quantum gates or quantum processors. You can create a egg curtain like structure where you would have atoms at each single lattice. They're all separated. You kind of create a potential well and put atom in each one of them. Then you individually send lasers to address each atom, change their state. You can make them interact. You can do gates operations. And that's also one of the ways where people are trying to create. It's just like creating a standing waves and modifying the standing waves such that you change the states of atoms and do quantum gates on this. So, okay. So using some of these gates and all these operations, and theoretically some of the algorithms, I think yesterday we had looked at the whole lot of problems which belongs to polynomial, non-deterministic polynomial, and NP-complete. Quantum, as of now, has helped to stretch beyond what is known to the classical physics. We have been established, or we have been told that there are n number of problems which are NP hard, but they can be solved using bounded quantum polynomial at a bounded quantum polynomial time. So some of the problems, not all NP problems have been shown to be solvable using quantum computers, but this is, I put it as a shady mark, which means that these are not like fixed defined. Today factoring, we know factoring can be done using quantum computers. We know many things can't be done, which means it's not that it's not doable at all. We still don't have algorithms, quantum algorithms developed for it. So there are a lot of algorithms need to be developed to be implemented on a quantum systems. So to expand this, nobody knows whether quantum computers can never solve NP-complete problems, but there are hopes. Many people believe that with time, you can develop algorithms to solve those set of classes problems also. Okay, so at this point, I think I'll take some questions and probably would like to break for lunch so that we'll come back in the afternoon with some quantum simulation things. Okay. So if you'd like to have any questions to be addressed.
Participants, do you have any doubts? Sir, thank you, sir. We will meet again on 2:30, sir.
Okay, yeah, thank you very much. Yeah.
Sir, one.
Yeah.
What is the
application I just saw at this moment?
What is the application?
Oh, I'm okay. My presentation. Okay. So, no. I think today I've been using different applications to make it. Today I think I used Keynote. Yesterday it was all LaTeX because if you have many formulas, it's always good to type in LaTeX and not I will only share PDF of all the talks.
Sir, everyone asking to share the presentation, sir.
Yeah, I'm going to share a PDF format of both the talks. I've given. I will ask you the talk of yesterday and today. Right? So that's what
Okay,
I'm
sir.
doing.
Thank you, sir. We'll meet again on 2:30.
At 2:30. Yeah. Okay. Thank you.
Sir, no need to mark the attendance for 2 sessions. It is enough to put one time in the morning, sir.
Okay, madam. Thank you.
Thank you. We will meet again on 2:30.
Madam,
Yes, sir.
we have to give the attendance at the end of the session right now, ma'am. End of the next session.
Yeah, afternoon session you have to mark the attendance.
Okay, now it's not mandatory right now, ma'am.
No need, no need. It is enough to put one time in the morning.
Okay, okay. Thank you, ma'am. Thank you very much.
Thank you, sir.